Figure 4 shows a sketch of the graph with equation y is equal to the modulus of 2x minus 3k, where k is a positive constant. So this is a transformation of a modulus x graph. It's been shifted to the right by a certain amount, and then it's been stretched horizontally by a scale factor a half. That's what makes it look like this. And then for part A, we're trying to sketch the graph with equation y is equal to f of x, where f of x is equal to k minus the modulus of 2x minus 3k. So there's a couple of transformations that have happened to this graph here to make it k minus the modulus of 2x minus 3k. We see the minus sign over here, we see the k over there. We need to think about what those two transformations are in order to sketch this new function. And when we sketch it, we want to state the coordinates of the maximum point, and we want to state the coordinates of any points where the graph cuts the coordinate axes, so the x and y intercepts. Okay, so let's think about the transformations that have happened to the modulus of 2x minus 3k. So again, we have the minus sign over here, we have the k over there. The first thing that we want to do is times everything by minus 1. And then that gives us minus the modulus of 2x minus 3k. So what does this do to the modulus function? Well, it would be a reflection in the x-axis. So when you're multiplying the entire function by minus 1, that will affect the y-coordinates. All the y-coordinates will get multiplied by minus 1, and that will reflect the modulus function in the x-axis. So it will look like an inverted V. This point here stays the same. The next transformation is then adding k. So we have k minus the modulus of 2x minus 3k. So adding k, what does that do? Well, first of all, to the function, it gives us exactly what we want. So minus 2x minus 3k, and then plus k. That is now the same thing as what we have over here. And in terms of the transformation, that will just move everything up by k places. So it's a vertical translation. If we add it to the entire function, it affects the y values. The whole graph moves up k places. So that gives us an idea as to what this graph looks like. So very quick, rough sketch. It gets reflected, and then the whole thing moves up by k places. So then that would look something like this. So what I'll do is I'll draw that larger and neater over here. So there is our modulus function. I've drawn it as two separate lines, a blue line and a purple line. Now what we're going to do is to work out the equations of these two lines over here. That will help us to work out the maximum point, which will be this point over here, and also the points where it crosses the coordinate axes. So that would be these 3 points. So these 3 points and this point, so there's 4 points overall we need to work out. So to get the equations of the two lines, the blue and the purple line, we want to consider this function over here. One of the equations of the lines would be k minus the positive of what's inside this modulus symbol, and the other line would be k minus the negative of what's inside this modulus symbol. So then let's start with the positive version of that. So y would be equal to k minus the positive of 2x minus 3k, so not changing the sign of what's inside the modulus symbol. This expands out to make k minus 2x plus 3k, and we can see from this that we have a negative gradient, therefore this must be the purple line over here. I'll just simplify that. That'll be y is equal to minus 2x plus 4k. So we have the equation of the purple line. And then for the other line, so now we consider the negative of what's inside the modulus symbol. So y is equal to k minus, so instead of 2x minus 3k, I'm going to times that by minus 1. That will then become minus 2x plus 3k. So just multiplying what's inside the modulus symbol by minus 1, that will give us the equation of the other line of the two that make up the modulus function. This is then k plus 2x minus 3k, and then expand this out. This is our blue line. It has a positive gradient, 2x minus 2k. Okay, I'll just put that on the graph. Okay, now we can start working out the various points. So let's start with the highest point. This is the maximum point. That was one of the things that we wanted to work out. So to work out this point, the easiest way to do that would be to just simply solve these two equations simultaneously. Set them equal to each other. That will give us this point over here. So that's 2x minus 2k is equal to minus 2x plus 4k. Blue is equal to purple. Solve that. We get 4x is equal to 6k. X is then equal to 3/2k. So that's the x coordinate for this point over here. Now we need to work out the y coordinate. we can work out the y coordinate by just simply plugging in this x coordinate into these two lines, or one of these two lines, and that will give us the y coordinate of this point. So I'll use this point over here, the 2x minus 2k. So y is equal to 2x, x is 3 over 2k, y is equal to 2x minus 2k times these two things out, you get 3k, and that will just give us k. So therefore, this point up here is 3 over 2k, k. So now we want to work out the intercepts of these two lines with the y-axis and the x-axis. So let's start with this point over here. This point we can get from the equation. This is the equation of a straight line. So y is equal to mx plus c. This must therefore be our y-intercept. So this point over here is minus 2k, or 0 minus 2k. And then to work out this point over here, so the x-intercept, we can just set y to be 0 for this equation. So that would be 2x minus 2k is 0. If you rearrange that, you end up with x is equal to k. So then this point over here would be k 0. And then for this point over here, we set the equation that we have over here equal to 0. So that would be minus 2x plus 4k equals 0. And when we rearrange this, we end up with x is equal to 2k. So this point over here is 2k, 0. And that is our final graph. That is our answer to part A. And now on to part B. Find in terms of k the set of values of x for which k minus the modulus of 2x minus 3k is greater than x minus k. So basically, on the left-hand side of this inequality, we have the modulus function. So we have what we sketched on the right-hand side over here. And then we're trying to see when that is greater than x minus k. So x minus k is the equation of a straight line. Let's draw this line on our graph, and then we want to see when the modulus function is greater than that line. Okay, so then to sketch y is equal to x minus k, we know that the y-intercept is minus k. So let's start with that. Y-intercept is minus k. That will be over here. So we know that this point is minus 2k. This point over here is minus 2k. That's the y-intercept. The y-intercept of this new line is minus k. It's therefore above that. So that coordinate is 0 minus k. And we also know that the gradient of this line that I'm going to draw in orange is 1. Going back to the equation, the gradient of this line would be 1 because of the 1x. So then it will be shallower than this line over here. This blue line has a gradient of 2. This line has a gradient of 1. The line that I'm about to sketch will therefore be shallower than this blue line. But the question is then, will it actually hit the modulus function, or will it just be a little bit shallower but still go above this point over here? Well, the easiest way to work that out is to work out what the x-intercept would be of this line of y is equal to x minus k. So I'll just quickly do that over here. If we consider y is equal to x minus k, if we work out the x-intercept, that's setting y to be 0. And then we end up with x is equal to k. So x is equal to k is over here. It's this blue point. So therefore we know that our orange line, y is equal to x minus k, also crosses through this point over here. So now let's do a rough sketch of that. So it looks something like this. And then we're trying to see where the modulus function is greater than the straight line. Going back to the inequality, when is the modulus function greater than the straight line? So what that basically means is, for a given x-coordinate, let's say like this x-coordinate over here, when is the output y value for the modulus function greater than the output y value for the line? So we can see that occurs over here. The modulus function is above the line. This whole region here actually is where the modulus function is above the line, where the y-coordinate is greater for a given x-coordinate. So then we're trying to work out the set of x values over which this is true. So what's the set of x values for which this modulus function is above this? That's what it says over here. So then the set of x values that satisfy the modulus function being above would be from here to here. So we know that this x value over here is k. What is this x value, well, we can get that by equating or solving simultaneously the equations of the orange line and the purple line. So the orange line was y is equal to x minus k, and then the purple line was y is equal to minus 2x plus 4k. Rearrange that, we get 3x is equal to 5k, so x is equal to 5/3 of k. Right, so that is this point over here. And then so that's our interval between k and 5/3 k, not including those two numbers, because if we look back at the inequality in the question, it says the modulus function is greater than x minus k, not equal to it, so we're not including k or 5/3 k in our final answer. So then our final answer would be, bear in mind in the question it says to give our answer in set notation, so our answer would then be k is less than x, which is less than 5/3 k, and then put it in set notation, so put the k colon in front, and then we have the squiggly brackets as well. And that'll be our final answer to part B. And then for part C, find in terms of k the coordinates of the minimum point of the graph with equation y is equal to 3 minus 5 lots of f over half of x. So there's 4 transformations that have happened here. We start with f of x, which is the blue and purple modulus function over here, and then we are doing a few things to that, applying a few transformations. The first transformation is this half over here, so that would basically stretch everything horizontally by a scale factor of 2. So then the graph pretty much looks the same, it just gets a bit wider. Then we have the minus 5 over here, so I'll group these two transformations into one thing. The 5 will stretch everything vertically, scale factor 5, and then the minus sign will reflect everything in the x-axis. So then so far, we've stretched everything horizontally, we've stretched it vertically as well, and then we have flipped everything vertically, so we've reflected the graph in the x-axis, and that would make it look something like this. And then the final transformation is the plus 3 that we have over here, so everything moves up by 3 places. So the graph still looks something like this, just a little bit higher. Okay, so then we can see from that graph that the minimum point is this point over here. And then so we're trying to work out the coordinates of that point. So this point here was this point over here. It was 3 over 2k, comma k. But after those transformations, it has turned into this. So then to work out the coordinates of the minimum point, let's apply these different transformations to that point of 3 over 2k, comma k, and that will give us this new point over here. Right, so I'll just write out the coordinate. So here is the coordinate for the old modulus function, and then this is the new function that we're trying to work out the new minimum point for. So let's apply these transformations to this point. So first, let's consider the half x that we have over here. So this will stretch everything scale factor 2 parallel to the x-axis, so that will multiply the x-coordinates by 2. So then our new x-coordinate would be 3k. Y-coordinate stays the same. Then we can apply the minus 5. We're multiplying the y-coordinates by minus 5. The y-coordinate was k, now it'll be minus 5k. And then the final transformation, this shift of 3 upwards, we're adding 3 to the y-coordinates, so this y-coordinate then becomes minus 5k plus 3, or 3 minus 5k. And that will be our final answer. This will be the new coordinate for the minimum point.